All right, Lucas, all yours. Thank you, sir.
Thank you. Hello to everyone. My name is Łukasz Czerwiński. I work at Backtoback company. This is a Polish startup located in Poland, in Krakow, and we are working with quantum algorithms. We tried to be platform and hardware independent, focusing on both implementing new algorithms and improving existing algorithms. So working with quantum, this presentation is available on our website. There is no link on the website nowhere, so you have to use this URL to get there. And it's publicly available for everyone. There is just no link to get there. You have to know an address. Today I'm going to discuss our tool, which is publicly available on GitHub. It's called Quasar. Probably each project in quantum world has to begin with upper Q or something like this. And we found a good name, Quasar, for it. Quasar is quite well documented on GitHub website how to use it. So I'm not going to show you a manual how to use it. I would rather to focus on something what is not available on GitHub. That means an algorithm behind Quasar. So I'm going to discuss how does a Quasar work internally. It's not available anywhere. You have to read code to find some details. What is Quasar? One more thing. If you get to these presentations, you can use page up and page down on this pad on the right down corner. So what is Quasar about? Working with quantum algorithm, we found that even a simple condition, like to check if some qubits are set and maybe one of many qubits is set only, we found that even if the code in Python is very short, it's not necessarily short using quantum assembly, like OpenQuasm, Qiskit, or whatever. You can observe that 3 lines of Python code are translated to 7 lines of code, and you can imagine that if we would like to change one qubit here, it would be a pain to rewrite all this sequence again and again. We found this task very tedious, laborious, and error-prone. That's why we implemented a tool. This is a Python script, and you can use a Python syntax to express some conditions over qubits, and this code will be generated for you. There is a clear split for front-end and back-end, so any code can be generated. It can be OpenPulse, it can be Qiskit, Cirq for Google, and so on. So this is motivation behind the project. This tool right now is mostly about if statements. Is not about loop yet. Probably we will implement a loop, but it's quite tricky. What does it mean, a loop within a quantum? But maybe it will be implemented someday. First, I'm going to tell you about intuition. It's like a very brief description. How does it work? First, using a Python syntax, we write some Python code. Here C1 and C2 means control qubits, control qubit 1, control qubit 2, whereas T is like target. So if both qubits are set, then execute X command on T1, Y command on T2, otherwise execute Z and H. Internally, within a quasar, it's represented as abstract syntax notation. The idea is to compute this condition and save a result in ancilla qubit. Then each line in then scope is executed if this ancilla is true. In qubit it means it's 1. And else scope is executed if ancilla is negated. This exclamation mark is not from Python, it's rather from C++, where it means negate a condition. During having this abstract syntax notation, having this different form of our program, we can quite easily generate low-level code using control version on corresponding commands. So if we used X, in generated commands we will find control X. If we use Y, in generated code we would find control Y, and so on. For else scope, ancilla qubit has to be negated, and it works. This is very higher level description. Now we are going to dig to details. Let's take a look how a simple if statement is represented as this abstract syntax notation. So we've got if with any condition, then 2 lines of quantum code. Otherwise, we've got 2 more lines of code. I told you that the condition is computed to ancilla. After execution is completed, we would like to revert ancilla to its previous state. It's always good to have ancilla in 0 state, clear state. That's why at the beginning we are uncomputing ancilla. This code is generated automatically by Quasar tool. Each line within then scope is executed only if this ancilla is true, is in 0, in 1 state. For else scope, ancilla is negated, exclamation mark again. So this is the way how can we represent this Python code in a more quantum way of writing code. Of course, in quantum assembly, there is no if-else statement. That's why this condition has to be repeated for each line of code. Here is a little bit more complicated example. We've got nested if-else statement. So condition 1 is computed to ancilla 1. At the end, ancilla 1 has to be uncomputed. Condition 2 is computed to ancilla 2. We need 1 more ancilla. Condition 3 is computed to ancilla 3, but I made a note at the bottom that because in this case ancilla 2 is reverted, it's clear, we can reuse it. On this example, on this snippet of code, I used another ancilla just to keep an example simple. But it can be reused, even it should be reused. Otherwise, we are using too many ancilla qubits.
I'm sorry if this is a silly question. What is uncompute?
What is uncompute? I will explain this further if you can wait.
Thank you.
But do you know what is a control X?
Yes.
So having some qubits like C1 and C2, computing ancilla is like control X, C1, C2 ancilla. There is a case when at the end ancilla will be not zero anymore. So if C1, if both C1 and C2 are set to state 1, ancilla will be in state 1. Uncomputing means revert these operations and revert ancilla to state 0. And there will be an example later on.
Thank you.
You're welcome. So code 1 is executed if condition 1 is satisfied and condition 2 is satisfied. That's why both ancillas have to be positive. Code 2 is executed if condition 1 is satisfied but condition 2 is not satisfied. That's why you can find here exclamation mark. For code 3, condition 1 has to be not satisfied. That's why ancilla 1 is negated. And ancilla 3 is positive. So it's quite a simple logic. I give you like a few seconds to take a look at this slide. Okay. If you have any questions, please interrupt me. But many things will be explained later. And one more example. Here code is even more deeply nested. So this code is executed if as condition 1 and condition 2 and condition 3, all of them are satisfied. Each condition is computed to ancilla. So we need 3 ancillas. And if all of them are true, then we execute code 1. Leaving this if statement, we are uncomputing ancilla 3. We are not using ancilla 3 this example anymore. And code 2 is executed if condition 1 is satisfied and condition 2 is not satisfied. So this is our intermediate representations. In Baytech we call it like abstract syntax notation. So if we have such a statement, if and a list of ancillas, then some code. Some ancillas can be positive, some ancillas can be negative. What do we do next? So if we have such a line, what do we do next? First, it would be nice to have all conditions positive. So we should cope with not control qubit 2 and not control qubit 4. How can we do it? It's not very difficult. It is enough to negate control 2 before, and at the end we have to revert it. It's not uncompute yet. This is just, we want to remove this exclamation mark. So for each qubit, which is with exclamation mark, we put it at the beginning with X command. And of course, because we've changed this qubit, we have to revert it back at the end. But doing these operations, we've got this line again, a little bit simplified, where all qubits are positive. We do not have negative conditions anymore. So what do we do next? We still have if line with many control qubits, then some code. In the simplest case, within a then scope, there is an unconditional command. By UT, I mean a quantum gate working on one qubit only, and this is unconditional quantum gate. So as a matrix, this is 2 by 2 matrix. And now we have some cases. Within if statement, there can be nothing. That means there is no conditions to execute this command. It means that command should be executed unconditionally. So if I have something like this within my abstract syntax notations, I can generate this code. It's the simplest case. Execute U gate on T qubit unconditionally. But I can have one control qubit, then execute UT. To implement this, we are promoting U quantum gate, which works on one qubit only, to another quantum gate in control version. So CU is a quantum gate working on 2 qubits. First is a control qubit, and this U is the same like this U. If I have 2 control qubits followed by unconditional gate, I can implement control U over these qubits. Or I can compute all of these are optimizations, or we can do it in a very naive way, a very simple way. We can compute all these qubits to ancilla, promote UT to control U with ancilla and the qubit T as a target, and we have to uncompute ancilla again. And later on I will give you an example of concrete uncomputing. So this is the simplest case where inside the then scope I've got unconditional command. But it can be a little bit more difficult. Inside a then command, I can have a conditional command. So I've got like 2 conditions. First is for this gate, apply this gate only if C is true or in one state, but there is one more condition from this. How can I do it? If condition is empty, I'm translating control U with control qubit and target qubit to the same. So I'm generating this piece of code. However, if I've got control U with one control qubit and one target qubit, and I know that there's one more control qubit, I can promote CU to CCU. That means control U gate. This is gate working on 3 qubits, so it's a matrix 8 by 8. And I'm using exactly the same qubits. Or I can compute all my qubits to ancilla. I can use the same command, but with ancilla. Please spot that Cn is a part of ancilla, and I'm uncomputing ancilla again. The most difficult and the last case is when I have control U command. And for example, in OpenQuasm in Qiskit, there is nothing more than control U command. If I have more control, I have to make a decomposition, and I will give you 2 different algorithms for decompositions later. so don't deal with this right now. So there is, how can I do it? If I've got a control U command working on 3 qubits, which is executed unconditionally, translation is very simple. I'm generating almost the same code. However, if I have a control U command with 2 qubits, and there is one more qubit in my if statement, I have to merge them together. So I'm computing C1 and C2 to Ancilla. Ancilla has a result on both of them, and I'm replacing C2 with Ancilla. So this control U is executed only if 3 of them, C1 and C2 and C3, are satisfied at the same time. I'm uncomputing Ancilla at the end to revert it to a 0 state 0. If I have more than one qubit inside if statement, I'm using the same algorithm. I'm computing Ancilla using C1, C2, and so on, together with Cn. Cn is here. I'm replacing Cn with Ancilla, and I'm doing uncomputing. And frankly speaking, there are no other cases. What can we get using this inside this abstract syntax notation? There is in Quasar there is also a command for flip. Flip is especially useful for Groover algorithm, and Quasar is translating this Python code into this abstract syntax notation, and it's very easy to generate quantum code from it. Okay, so you have an idea. I used many times something like condition and compute condition to Ancilla. Now I'm going to explain what kind of conditions are supported, and I'm going to explain you what does it mean to compute, and later on what does it mean to uncompute. So first condition, which was already visible on the second slide, is all. It means that all qubits have to be in one state. And if all of them are satisfied, execute code 1. This can be computed using control using qubits. Control1 command is easy. Control X is easy. Control X is also easy because both of them are supported by Qiskit and OpenQuar. However, if I have more than 2 control qubits, I have to make a decomposition. So right now, stay with this fancy function name, control .x for a moment, but I will explain how can we implement this step as well. So all is simple. All means make a multi-control X on all these qubits. Very often for multi-control X, uncomputing is the same, but it's not always true. So another condition is 0. That means that all qubits have to be in a 0 state. It's completely different than a previous condition. How can we do it? These 3 lines are the same, but first we have to negate all qubits, and after all we have to revert all qubits. So 0 is like negate all qubits and check against all conditions. Another condition is any, and any can be implemented as non-zero. Sorry, this not is invalid. Let's assume this not is not here. Any means that in a set of qubits, in a collection of qubits, at least one has to be satisfied. That's why any can be translated as not zero. This is an algorithm for zero, and there is one difference only, this exclamation mark. So this exclamation mark comes from this not, and this not is a mistake, it should not be here. Another condition is match. Match takes a collection of qubits, it takes a collection of bits, 1 and 0, and if it checks if qubits are, for example, I know you don't see my screen, so let's use this web browser as a notepad. So if match Q1, Q2, Q3, 1, 0, 1. This is a use case, how can we do this? If mask is all 0, we can very easily get a 0 condition. If mask is all 1s, we can very easily get all condition. So match is a very powerful condition. We can implement almost any other condition within this one. The last but not least is a not. Not means negate a condition, and it's just an extra exclamation mark with ancilla. Okay, I told you that there is this fancy function control .x. In IBM Qiskit library, this is known as multi-control toffoli. So, can you see my web browser?
Yes.
Multi-control, okay, not this one, MCT. MCT is exactly this function. It's a multi-control toffoli. It takes control qubits, one target qubits, and it makes the composition. And now I'm going to show you two different algorithms for the composition. First, it's very simple. It's called VChain. This is on the left-hand side. You can very easily spot where does the name come from. We are using some ancillas for a partial result, but we can draw this as a V. That's why this is a VChain. Here we've got X commands, and here we've got U. This U comes from our command, so it can be control, X, Z, Hadamard, and so on.
Lucas, we're losing your volume a little bit.
Okay, I tried to speak louder.
Just a second ago, yeah.
On the right-hand side, we've got almost the same algorithm, but in a much more dense representation. We still need two ancillas, and we still need 5 control gates. So it's not more optimal, it's just a different order of computation. And now I will try to answer a question: what does it mean to uncompute? This is ancilla qubit. Ancilla qubit is not a user qubit. but this is a temporary qubit we need for a computation. As you see on the previous slides, I'm not using Ancilla directly. Ancilla is only used in generated code, so very rarely I'm using Ancilla. If you have some experience in C++, we can say that Ancilla is a temporary expression. So we do not use them, compiler does it for us. Initially, Ancilla is in a zero state, and after this command, Ancilla can be changed. If we leave Ancilla in non-zero state, we can't use it anymore. We can, but it's much more tricky. For us, very convenient is to revert Ancilla to its previous state. So in this moment before and in this moment after, we would like to have Ancilla in zero state. That's why this part is uncomputing. We would like to have Ancilla clear. Did I answer your question?
Yes, thank you.
We are doing uncomputing for each Ancilla because we want to have all Ancillas cleared at the end. This algorithm is very simple, but it has some drawback. We need more Ancillas. And probably you are aware that currently quantum computers do not have many Ancillas, many qubits. So qubits are a very worth asset, and we don't want to use many Ancillas. That's why there's another algorithm, a little bit more complicated, which is not using Ancillas. However, it generates much bigger circuit, much bigger output. This algorithm has a recursive definition. So given a control command, we are using a decomposition. We are using control with one less qubit command. So like 1, 2, 3, 4. So in decomposition, we are using only 1, 2, 3. So with one qubit less, one condition less. But we are using such a function, such a gate, 3 times. In addition, we are using 2 control gates, which are easy because almost any quantum assembly language supports control command with 1 qubit only. And we are repeating this algorithm until we reach a recursion end. That means control command, control U. This is a stop condition for our recursion. We know how to do it. We do not make any recursion call anymore. You can observe that these pictures are almost the same, just this line is duplicated many times. It's quite easy to remember. What's going on here? So, if a second qubit is satisfied, we apply a V. And if the first qubit is satisfied, we apply V again. Applying V 2 times is the same like applying U 1 time. This V plus this V is the same like this U. However, there is a case when only 1 qubit is applied. So we have to so we can split this into 3 steps. The first step, a second step, and a third step. An interesting thing is that we can permutate these steps and it works in any order. So if we have only one qubit in one state, U is not exactly what we wanted. That's why we have to revert this command. This star means dagger and it means a reversion. So the transpose conjugate of this matrix. And this makes XOR. So we can translate this simple circuit as if the first qubit is true, make half of the job. If the second qubit is true, make a second part of the job. If both were true, you are done. But if only one of them is true, you did half of the job unnecessarily. XOR is a good way to check if only one of them is satisfied. So if one of them is satisfied, undo half of the job and uncompute revert the state. I believe it's not obvious at the first moment, but I believe that if you already know this algorithm is quite easy, but if you don't know, don't worry, you can play with it and figure it out how does it work. Okay. Here is a progress bar, so you can see we are almost at the end. Now we talk about some optimization. I told you that the condition is computed to ancilla. At the end, ancilla is uncomputed. And I told you that if is controlled by ancilla. Using this very naive algorithm, we are generating such a code. Calculate ancilla using a C qubit. For CX command, uncomputing is exactly the same. So this is computing, this is uncomputing. And by chance, by accident, this is the same expression. And using ancilla, execute this command. So X is promoted to its control version, control X, with ancilla to T. In the first implementation, Quasar generated 3 lines of code. And of course, we would like to have our program as short as possible. That's why we would like to have this condition instead. Such a simple statement that we know it's the control X with C as a control qubit, T and the target qubit. No need for this intermediate steps. And the same applies for control version. If C1, C2, T, no need for 3 quantum gates, 1 quantum gate is enough. That's why in the second version of Quasar, which is unfortunately not available yet on GitHub, but it will be soon, we've implemented further optimization. So, Control X something to ancilla, Control X ancilla on target, and uncompute Control X can be represented as this diagram. We can detect such a combination of 3 gates. It's not difficult. And we can replace all of them with 1 gate only. However, it can be done only when at t time 0, this line is like a slider and points some time at the beginning. We can do this optimization only if ancilla is in 0 state. otherwise it's not working. So if there were Hadamard somewhere before gate applied on Ancilla, this is not a correct expression, and we can't do this optimization. The same is on my right hand side with Control-X command. Only if Ancilla is in 0 state, we can find this pattern, and we can simply replace this with such a gate. It's much shorter. And one more optimization. You can recognize this part as computation, compute some condition to Ancilla, execute some quantum gates depending on Ancilla, and make uncomputation. These adjacent gates in the quantum vocabulary are called as back-to-back gates, and very often we can remove them. It's not always a case. It works for the Pauli gates, X, Y, Z, Hadamard. It's not always true for rotation. We can replace these gates only if let me use a text editor again. So U1.U2 has to be equal identity. So if these two gates satisfy that condition, it means that I believe they are called evolutional. Let me check it. It's something with evolution. Forgive me. It has its own name. And it's not evolution, it's evolution. Evolutional gates. It has to collapse to identity. But then we can apply this optimization. And that's all. This is the last slide of my presentation. I'm happy to answer all your questions right now.
It might be named that because the Hermitian conjugate is an involution in the algebra.
Okay.
You know, this has certainly given me a perspective that I hadn't thought of yet. So thanks for that. I can't wait until, you know, as you were talking and I'm trying to understand this, just imagining the issues of doing loops, you know, as you indicated at the very start.
Probably not.
I mean, you know, you start having to deal with stacks and potentially recursion and all kinds of crazy things.
It's even hard to imagine what does a loop mean in quantum world.
Well, even just in practice. I mean, you know, what would that mean, and just theoretically? But you've introduced a way to put in if statements. No question about that. Interesting. Are you finding folks out there taking interest in into this capability, or are people still just kind of doing it themselves? Or, I mean, is there, I don't know the algorithms well enough to begin to speculate really on this. How useful is this in algorithm development at
Okay,
this point in time?
you've got a real example of Groover implementation. For example, if you want to flip one state in Groover, it is enough to write such a line of code. If predicate and predicate is an oracle, if predicate is satisfied, flip, that's all. And this is mirroring operation. So it's not depending on predicate, is not depending on oracle. It has to be zeros everywhere. So you can express your algorithm in a more high-level way.
Yeah.
You do not play with control qubits. It was pain. Here is a Fourier. It is a real example of how can we use Quasar. You can even understand how does it work. And in this case, for going back to Groover, it takes qubits and it takes predicate, and predicate is a match 0, 1, 0. So this Groover is searching, is doing a search on 3 qubits, and we are going to find this qubit sequence. It helped us a lot answering your question. Can you imagine writing such a code or fixing it? It was really pain. And it is not a complicated statement.
Yeah. Okay, any comments, questions, folks? It's a lot easier to ask in person than going to Reddit or whatever people use.
It's a very ingenious way of getting around what functional programmers would hate about quantum, which is that your bits change as you go. You cannot test a bit without changing it. This is very ingenious.
Yeah, in some strange way, it reminds me of going from the go-to statements that we used to have back in the 70s to the notion of a function. You know?
Of course, it's invalid to write such a code if Q1, then X Q1 is an invalid statement. You can't control and change the same qubit. It has to be something different. The only exception is Z. It works for Z and anything else. I'm not sure if this condition is inside Quasar. It should be there. It's not allowed to control and target the same qubit. And going back to functional programming, my first attempt was to implement this in Haskell, but I'm much more familiar in Python, and we are using Python in BATE. I moved from C++ to Python recently, and I really enjoyed. That's why Quasar is in Python.
Yeah. Python is agnostic about functional, imperative, or object-oriented.
Yes. But you can write pseudocode and it works.
Yes.
Okay, last call, folks. Don't want to hold Lucas up. He's still got, it looks like he still has a little bit of sunlight behind him. Just a
You
little
can
bit.
always reach me on Tech website.
Cool. Thank you. Yeah. Yeah. And I've got the link to the presentation and to the GitHub available. I put it in the chat, so you've got it. You don't have to type it in. But it's good to have that out there. This is the kind of thing I know I'll come back to at a later point, I'm sure.
And the new Quasar is going on, so stay tuned.
And so will you call it New Quasar?
No,
Quasar?
it's just a Quasar version 2.0.
Oh, come on, give it a cool name. Talk to management about that.
Okay.
Quasar is rule. Super, super bright.
Yeah, so something along that line.
So you can really very easily create a fancy name in quantum world. Have you heard about Quasm? Open Quasm?
Yeah, the simulator?
Yes.
Yeah.
Or condition for Quasm, and everyone is laughing. So in quantum you can create fancy name very easily.
Hey, you're talking to the inventor of Quantumapalooza. I've got
Thank
another
you for
one.
your
Yeah.
okay, thank you for your
Lucas.
attention,
Yeah,
and have a lovely day.
Yep. Thank you, Lucas. Thanks to everybody for coming out. I'm sure this is one of those you want to keep in the back of your mind and explore again later. And we'll watch out for Quasar 2 or whatever you happen to call it.
There is a chat. Sorry for it. I missed chat.
Oh, no, that was just some background stuff there. You're okay. We're good.
Goodbye.
Thanks again for your flexibility, Lucas. I really appreciate it. Might screw up there, but it came out okay, I think. So everybody else, thanks for coming by today. Actually, you know, Philadelphia Harrisburg's taking a week off next week by accident. I don't know how it happened, but Monday in particular, as I said, nobody anywhere in the world is having a quantum event. So maybe get some sleep or maybe find some time to actually get your hands in the code in the meantime. So thanks for coming by, everybody. Lucas, again, you know, maybe when Quasar 2 comes out, maybe we'll have you come back again if you have the time and energy. I'd like to see what the improvements are. I want to see if you have a recursive loop in there.
No. From user point of view, API is almost the same. We implemented much more quantum gates, and we implemented much fancy optimization.
Alrighty. Maybe if you change your mind.
No loop yet.
Okay, thanks, Lucas. Everybody else, thanks a lot, and everybody have a great weekend. See you later.